Okay, in this class we're going to look at solving second order differential equations, this time using a combination of v substitution and the chain rule. Okay, so the chain rule, I'm writing this version of it. It says if f of x is equal to u of v of x. So f is some composite function made up of two different functions called u and v. The variable is x. Well, then f prime of x can be written as du dv times dv dx. So to take the derivative of a composite function, we take the derivative of the outside function first, and then we multiply it by the derivative of the inside function. Okay, so the derivative of u with respect to v, and then the derivative of v with respect to x. Okay, du dv times dv dx. And that's important. This is the version that's in your formula and tables booklets. This uses Leibniz notation. Okay, this is Leibniz notation as opposed to this version, which uses function notation. I want to talk a little bit about cancellation and the multiplication of fractions. So if I multiply 2/3 by 3/5, what we'll get is the 3's will cancel to get 2/5. And any time you're multiplying two fractions where the denominator of one is equal to the numerator of the other, those two things will cancel. So 2/3 times 5/2, the 2's will cancel to give me 5/3. 7/8 times 8/5, the 8's will cancel to leave me with 7/5. 11/13 times 3/11 is 3/13, and this extends into derivatives, which are just fractions. dy dx times dx dt, the dx's will cancel to give me dy dt. dy dx times dv dy, the y differentials will cancel to leave me with dv dx. ds dt times dt dv, the dt's will cancel to leave me with ds dv. And then finally, in the last example, the or differentials will cancel to leave me with dv with dt. Okay, this is just the chain rule. That's what the chain rule says. Okay, it's just essentially dealing with the multiplication of fractions. Okay, so we're going to look at using a v substitution and the chain rule together. In our previous examples, when we had a second derivative as a function of the first derivative, we were using a v substitution on its own. Now we're going to use that with a combination of the chain rule. And the process is as follows. We let v equal dy dx. And then we take a derivative with respect to x on both sides, giving me dv dx equals d2y dx squared. Okay, and this is, this is not complete. But, if I substitute dv dx in here at this stage, dv dx equals f times y, that leaves me with three variables, a v and an x and a y. So let me actually look at that. Suppose I now said dv dx equals f of y. Well, that's a bit of a problem, because now I have v, variable x, and variable y. It's actually more complicated than what we had originally because we have three variables. However, I'm going to use a little kind of trick here with the chain rule. I'm going to say that dv dx is equal to dy dx times dv dy. The chain rule says that dv dx is equal to dy dx times dv dy. Okay, or if you like, the cancellation in fractions, the dy's would cancel to leave me with dv dx. Now, why is that useful? I still have three variables. Well, it's useful because v is equal to dy dx, so I can substitute a v in here. So that's going to become v times dv dy is equal to some function of y. Okay, and that's going to be useful for differential equations of this type. Okay, notice we've only got two variables here and here, v and y. So that's going to be my substitution, and go through that, make sure you understand where everything is coming from. So what we'll do is we'll say VD is equal to f of y. So if we get something like this, we're always going to change it into VD will be equal to whatever that function of y is. Okay, so I'm going to look at one example here and see how this goes. I'm going to say I want to solve this differential equation. Given that y equals, that should be y equals 1, I'm going to just change that to y equals 1. And dy dx is equal to 1 when x is equal to 0. So that's what I want to say. So I want to solve this differential equation. d2y dx squared equals y, given y equals 1, and dy dx equals 1 when x equals 0. So I'm going to go through this full thing from start to finish. Again, we're going to use a combination of the v substitution and the chain rule. So we're going to start. Let v equals dy dx, and if v is equal to dy dx, then taking a derivative with respect to x on both sides will give me dv dx equals d2y dx squared. Okay. Remember that dv dx, now we have variables v and x and y, so I'm going to just do something here with this, and I'm going to take that dv dx and I'm going to write it as dy dx multiplied by something equals to d2y dx squared. Okay, dy dx times some fraction has to give me dv dx. So what can we do? Well, you know, in order to use the cancellation and multiplications, I want to get dv on the top, so that's going to be up there. I want to cancel the dy's, so that's going to be a dy down there. Okay, so dv dx is the same exact thing as dy dx times dv dy. So what we have here is that the second derivative, d2y dx squared, can be written as dy dx. Now dy dx here, remember that dy dx is just equal to v. So that's equal to v times dv dy. And that's my substitution. So my substitution is going to be to take this value for d2y dx squared, v dv dy, and plug it in here. Okay, scrolling down the page. So substituting in, we're going to get v dv dy from my original equation. That's replacing the d2y dx squared, the second derivative, and that's equal to here, that's equal to y. And this is now a first order differential equation. I can solve it. How do I solve it? I'm just going to multiply on both sides by dy. v dv is going to equal to y dy. I'm going to take antiderivatives on both sides. I'm taking the antiderivative there, we're going to get v squared over 2 is equal to y squared over 2 plus c. That's a general solution. In order to find a particular solution, I've got to examine my initial conditions. But, so go back to my question here. What do we know? Well, what do we know? We know that v is equal to dy dx, and we know that's equal to 1 when y is equal to 1. But y is equal to 1 when dy dx is equal to 1. So y is equal to 1 when v is equal to 1. Therefore, substituting 1 in for v, we get a half. Substituting 1 in for y, we get a half, plus c. So we can conclude there that c has to be equal to 0. Which means that v squared over 2 is equal to y squared over 2 plus c, which is 0. Doubling both sides tells me v squared is equal to y squared. And again, solving there for v, that means that v has to be equal to either positive or negative, whatever y is. If v squared is equal to y squared, then v could be the same as y or just the opposite to y. Remember, the squares of opposites give the same thing as well. Negative 2 squared gives me the same as 2 squared. But again, we're going to look at our initial conditions again. V is equal to 1 when y is equal to 1. So we can discount the negative. We can't say 1 is equal to negative 1. So we can just have v is equal to positive y. That's my new differential equation. Okay, why is it a differential equation? Because it contains a derivative. What is the derivative? Well, remember, v, right back, that was our original substitution. Scrolling back up the page, v is equal to dy dx here. So we can kind of unsubstitute, if you like, at this stage. So v is the same as dy dx. So now I have dy dx is equal to y. And I'm going to solve this equation. dy dx is equal to y. Solving dy dx is equal to y. Dividing on both sides by y. 1 over y dy is equal to dx. Taking the antiderivative on both sides gives me the natural log of the absolute value of y is equal to x plus c. Okay, go back to my initial conditions. But y equals something when x equals something. Check back to the start of your question. I'll scroll back up very quickly. But y is equal to 1 when x is equal to 0. So we're given that information. Y is equal to 1 when x is equal to 0. That means the natural log of the absolute value of 1, which is just 1, is equal to 0 plus c, which is c. The natural log of 1 is the exponent to which e is raised in order to get 1. It is 0. Therefore, the natural log of the absolute value of y is equal to x plus 0, or just x. Which means the absolute value of y is equal to, well, what's this saying? This is saying that x is the natural log, the exponent to which e is raised in order to get the absolute value of y. Which means, again, two possible solutions for y. Y is equal to plus or minus e to the power of x. But again, I'm going to check both of those solutions as I've done before. We know that y has to equal to 1 when x equals 0. Therefore, y must equal to, well, if it was plus e to the power of x, positive e to the power of 0 is 1, so that's good. But if it was negative e to the power of x, negative e to the power of 0 is negative 1. That wouldn't work. So y has to equal to e to the power of x, and that's my solution. And that is how we solve a second order differential equation with v substitution and the chain rule. Okay, let me very quickly run through all the various steps. So, first thing is to note it's a second derivative in terms of the variable on top, y, not in terms of the first derivative. I'm going to use a v substitution, set v equal to the first derivative, take a derivative on both sides, use the chain rule, and ultimately come up with v dv dy. v dv dy. Okay. So that's important. That's what we're going to do. So one thing, you can commit this to memory if you want, but do go through the process, understanding the logic. I've never committed this to memory, because my brain doesn't work that way. But if v is equal to dy dx, then v dv dy is equal to the second derivative. Okay, so you could commit that to memory and just make that substitution straight in. My brain doesn't work like that. I like to derive this value for d2y dx squared all the time. Okay, substitute it in. Now we have our first order. Separate, integrate, use your initial conditions to solve, find a particular solution. Okay, notice we got two values for y. V could be plus or minus y, but it has to satisfy the initial conditions. So we're able to eliminate v equals negative y and keep v equals positive y. Remember, v is a first derivative, dy dx. So unsubstitute in there. We have dy dx equals y. Separate. and integrate, and again apply our initial conditions to find the particular solution, we're able to find that y could be plus or minus e to the power of x, and then again check both of those, again have to satisfy your initial conditions. Y is positive 1 when x is equal to 0. Well, that does not satisfy both of these. In fact, it eliminates the negative e to the power of x. So my final answer, y equals e to the power of x. So practice, practice, practice.